one more step with this, and this is where I try to wow everyone. Not sure if this is going to actually happen, but when we look at these two anomers here, so they're stereoisomers, and they're formed, I should say, by this hydroxyl group pointing back to the upper right, attacking from either side of the carbonyl group, and we get the beta and the alpha. And then in reality, as I shown here, these are all equilibrium reactions. And so you can form the alpha and the beta. This will actually go backwards, can break apart into the acyclic form. And all of these steps are in equilibrium. The sugar is going back and forth between the acyclic and acyclic form. So in water, they're actually not formed to equal extents. However, the beta form accounts for about close to 70% of the conformation, and the alpha, I think that should be 33%, is the remaining. In other words, the beta conformation here, this one with the OH group pointing up, is the preferred conformation. So now we want to, the last step is ask the question as to why. Why is the beta conformation preferred? And this was actually semi-fun because it's showing there's one thing yet that's missing. So we've gone from this acyclic Fischer projection now to these cyclic structures here. This is what's known as the Haworth projection. Notice it's a six-membered ring decorated with all these hydroxyl groups. Here's our anomeric carbon. And we know back from the good old days in Organic 1 that this representation here, even this flat representation of the six-membered ring, is not capturing all of the structural details. And instead, what we really need to do is to turn this into the chair conformation. So let's do that and see if that can provide any insight as to why we get this preference for the beta conformation. Because this is extremely messy, I'm going to scroll up here. Probably shouldn't have had it so cut those lines off, but why don't we put it down below where those lines are and see if this makes sense. So we want to convert to the chair conformation. So now in this particular case, let's redraw the beta. So if it's okay, I'm going to scroll up like this. See if I can actually draw it better with my hands, slightly more on an iPad. No, not really. It's like I know what I'll be doing to practice one more time. So we'll go with that. So this is our beta. The hydroxyl group is pointing up. These are all defined by glucose. I'm going to condense that CH2OH down. So going back, this structure down here in the bottom bottom left is the same as this structure up here in the top amongst all this other stuff. So this is the beta conformation. Now, let's turn this into the chair conformation. And so the way to do that is, we'll just stick with this magenta here. What we want to do is essentially take this carbon over here, the anomeric one, and pull that down. And then we're going to take this carbon over here on the left side, carbon 4, and pull that one up. And so that should give us the chair conformation. So let's see if I can actually draw this. So it has something that looks like this. And now what we need to do is this carbon here, with a little dot on it, this is our anomeric carbon here, is the one that we had pulled down. And then this carbon back here, carbon 4, here, this is the carbon that we pulled up to get us into the chair conformation. So now let's fill in our substituents. So remember, in the chair conformation, at every position, there's something that's axial and there's something that's equatorial. And in this particular carbon in the anomeric position, we'll just draw both substituents here. What's pointing down is axial. What's pointing up on the ring, pointing up here, is in the equatorial position. this hydroxyl group here is pointing up, so there's our hydroxyl group. We'll just put the hydrogen in on this one. So now we go to the next carbon, this hydroxyl group over here. And why don't I put the numbers in, actually, just to keep track of things. We'll call this carbon anomeric, we'll call it 1, 2, 3, 4. So it's 5, and then our oxygen is 6. Oops, and if I'm doing that, let's number these. Let's have 1, 2, 3, 4, 5, and 6. So carbon 2 here, the hydroxyl group is pointing down. So that's in that position. Carbon 3, the hydroxyl group is pointing up. 4, it's pointing down. And then 5, it's pointing up. So I'll encourage you, if needed, to go back and to review, how this is situated around the chair conformation with axial and equatorial. And while we're at this, here, let's do the same thing for the alpha, and then we'll compare the two. So the alpha Haworth projection. Oh, now we got really long. Okay. Everything is the same here. Only difference is that this hydroxyl group is pointing down or opposite trans of the CH2OH. Now if we were to do the same, pulling up, pulling down to get the chair conformation, now this anomeric carbon, the hydroxyl group is pointing down. Carbon 2, the hydroxyl group, so what to highlight here. Carbon 2, the hydroxyl group is also pointing down, so these are all just like before. Up, down, CH2OH. The only difference here is the anomeric position. And then now, finally, this is supposed to be the big aha moment, is that the beta conformation seems to be preferred. It's the major one. So why might that be? Notice here in glucose, all of these substituents are equatorial here. Equatorial, 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 equatorial. The only difference between alpha and beta is that this hydroxyl group is now axial. Remember, in general, having the larger groups at the equatorial position are energetically favored. And actually, beta glucose has every functional group in the equatorial position. The alpha conformation has every group except one in the equatorial position. So by having this hydroxyl group in the equatorial position, maybe that's energetically favorable, and that's why the beta conformation is preferred. So question about the hydroxyl and the CH2OH electron densities. Are you asking about the alpha and the beta nomenclature?
I think they typed in that answer after you mentioned why is the beta favored over the alpha.
Oh, okay. Yeah, and so this is where I'm hoping everyone is like, wow, that's fantastic. That makes sense. Is that the beta conformation? Yes. So you're right. So the conformation, in order to, let me start over here. When we form the cyclic structures here, first of all, on the right here, on the top now, we end up forming this new chiral center. And then if we look at a little bit more detail here, we would notice that we have the two different stereoisomers. They happen to be called anomers in this case, where the hydroxyl group is pointing up and the hydroxyl group is pointing down. Then the observation is that the beta anomer is the preferred anomer. So then the question is, why is the beta anomer actually preferred? And this has to deal with the density, yes, of the OH and the CH2OH. And really to visualize that, then we need to look and say, well, actually this six-membered ring here, this structure that I'm just randomly circling here, doesn't capture what it actually looks like. And we know that a conformation of which the structure exists in is the chair conformation, that it minimizes those steric and torsional interactions. So if we scroll down further and we go through this really scribbled out attempt of showing what the beta and the alpha conformations look like, we will see that, yes, actually in the beta conformation, all of the hydraulic groups are actually in the equatorial, or the more favorable, generally more favorable position that we have here. And that provides a structural explanation for why the beta anomer is the preferred one. And then, Crystal, I'll get to your question in a second here about the different positions. There's one more thing while I'm on this kind of like soapbox here. If you find it interesting, it's that two of the most common sugars that are out there are fructose and glucose, and we can show glucose or ribose here in a second. It's kind of interesting that the sugar that's used so much in biochemistry actually happens to be a six-membered ring, so it's glucose. So maybe there's a reason why nature actually selected to use glucose for so many different reasons, because it is relatively stable. It can adopt the chair conformation, have all of these groups in the equatorial position, but is also existing in a relatively energetically favorable way to go back and forth between the acyclic and the cyclic form as well. Okay, so now a couple of questions that we need to address. Okay, excellent. So there's hopefully a nice logical story there. I know it takes to get to the very end to see everything unfold. So let's go through the rotation and axial and equatorial in those conformations. So actually, I'll show the rotation first, because I think that was the first step. I'm going to scroll back up again. And this blue arrow, I'm sorry, was it the blue or the purple one that you're interested in? Trying to use these pastel colors to make it look fancy. The purple one, so the rotation. Oh, I see. I sorry what you're saying. So what I'm doing here, in this particular case, actually, just 1 second. At the bottom here. Okay. So this will lead into the other questions.